Thanks everybody for joining us today for this next talk in the complex series. Just a quick note about the slide material for today. So there's actually I was preparing to get ready for the talk today, and I noticed we had done some sort of semi-automated reformatting of the slides recently to include some standard sort of grant information at the bottom of each slide, as you see here. But that seemed to have sort of mangled at least this talk as far as I can tell a bit in terms of the formatting. So I think that mangled version is the one that Cindy has posted in the chat, the link to. So just want to make that note. I also noticed, so you can find all of our material as well posted on our new revamped SDSC website in the On-Demand Learning Center. And there'll be links to previous materials as well. So I'm going to go off one of the older versions of the slides, just it's a little bit clearer to read in some cases. However, I did notice whoever formatted this one also not able to click on the links that are actually in the slides. So you might want to get copies of both, but we'll try to get this sorted out on the website and what's posted where sometime after the talk today. So just want to make that note if you come across anything sort of odd in the slide deck that you might have the link to at this time. Okay, so let me go ahead and stop full screen sharing just with that note and share the individual talk here. Go to slideshow. Okay. So as we go through the talk today, feel free to drop any questions as they come up in the chat. I'll try to pause here and there to see if anything has come up and answer your question as we go. If not, there's, as I think Cindy mentioned, we always have roughly a 30-minute window after the talk to answer any questions you have about the talk or other things that you might have want to discuss that sort of comes to mind while you're with us today. Okay, so today's talk is on data transfer. Hopefully that's the one you're here for. And if you haven't been to a complex talk before, this is a new training program we started last year. So this is sort of the beginning of our second year that's funded by the NSF. And the idea for the complex project is to pull together the type of training material for users of high performance computing systems that aren't necessarily developing their own code, but might be using like code in a different lab to do simulations or data analysis. And so they have their very specific use cases, but we want to try to teach you about the different tools and techniques around high performance computing that you need to learn, even if you're not like necessarily a programmer or developer per se, right? So these are just sort of command line tools and other software that and techniques that you might employ in your research to develop your workflows for your own science. And so that's sort of the idea about the complex project. This talk is sort of intended to be the first in a series on sort of data management more broadly. And so this is the data transfer talk. We did do part 2 last year. So if you're curious about sort of fast forwarding and not waiting for the second part of the talk later this year, it should be posted in the data storage and file systems talk. Recording and slides is available, should be available now in the online learning center that I just showed you. The parallel IO one is still under development, and so we'll present that at some time in the future. But this is sort of the data management series of the complex project here. Now, of course, data management is like a huge topic. It's a field in itself. We're really focused on the core in this diagram of like just basic data management, safety, security, and the options of how you actually and where you store your data and how to organize it, sort of in that core section. But if you have complex data management challenges, many universities have experts at your institutions who sort of understand this more complex workflow of all the different facets of managing data throughout the research lifecycle. And put a link here to the Harvard Biomedical Data Management website, which has lots of good resources there that where I got this diagram. So there's lots of stuff out there online, but also you probably have some experts at your institution as well you can talk to about more complex things with regards to data management. So the goal for this talk is really to get new users of high performance computing systems familiar with how to get your data to and from, say, your laptop or your lab research workstation to an HPC system, and some of the other things around that sort of basic workflow that you might want to use and employ in your day-to-day activities, right? So this is sort of the basic set of learning goals that the talk goes through. It's really mostly an overview of different tools and what they're used for, and sort of the most common ones that are available that you'll come across when you start getting familiar with transferring your data to and from HPC systems. And the prerequisite knowledge here, I put a link to some of the other complex materials or complex webinars that we have. So this really assumes that you have some basic, understanding of Linux and shell programming, command line tools, essentially. Because most of the tools we'll talk about, they're all sort of command line driven for the most part. This is just sort of a general disclaimer for most of the talks that I give in the complex series or in general for our HPC users. HPC runs on Linux, and so most of the tools that we cover are sort of Linux or Unix-based command line tools or compatible tools. Many of these tools have either exactly the same or equivalent versions in Mac OS these days. So if you're Linux or Mac OS users, you'll probably find these things natively on your system, or can install them very easily. Of course, for Windows users, it's a bit more complicated, but if you haven't ever played around with the Windows subsystem for Linux, this is sort of what I recommend for Windows users who want to get more familiar with Linux as they get more involved in doing high performance computing. That's sort of the best method out there, I think, or option available for you on your Windows system that I would recommend checking out if you haven't previously. Now, okay, so today is the data transfer talk. So the key things to keep in mind when we're talking about data transfer, it's really usually synonymous with transferring files for the most part, right? So that's, even though it's sort of a data transfer can refer to a broader scope of data movement activities. Usually when we start off talking about data transfer and between, wherever your data is living to an HPC system, it's usually talking about file transfers, right? And so that's mostly what we're going to cover today. And the thing about doing, and so people use these terms interchangeably. Data transfer is usually just referring to a file transfer, right? So I'll use those terms pretty interchangeably today. Now, the key things to think about when you're transferring data or transferring files from one system to another is really these, I think, 5 key points to always keep in mind before you transfer data, especially if it's a lot of data and it's very complicated in terms of the organization structure and how much you need to move between different systems. These are the types of questions you want to ask yourself, sort of like, where is the data located? How is the data organized is important. And I'll show you, how much data, obviously, do you have to transfer? Where's the data going to go? And sort of then those questions sort of lead into the final ones, like how should you transfer that data, right? Like what tool or protocol do you want to use to transfer those files from one system to another, right? And of course, there's this little cartoon here. There's lots of things that go on in a file transfer, right? There's the type of files. There might be, is the file encrypted while it's traveling from your desktop system, your client system, to the server, which is sort of the HPC resource you might want to get to. It's going over the internet. So there's, again, the encryption, decryption aspects of things. But again, to keep in mind things of where is the data located now and where it's going is also important because the characteristics of your own laptop or desktop and the pipes that the data is going to go through to the end service and where that data is going to physically get stored on the other end is also important in understanding sort of the performance characteristics and how much data is going to be transferred and how fast it's going to get transferred. So each one of these little elements in the cartoon are actually very important to determining the overall sort of throughput of the transfers and sort of uh, you know, which is why these questions are important, essentially. So this is sort of the outline for today's talk. Again, it's going to be a very sort of maybe too much of an overview of just, hey, there's this tool, there's this tool, there's this tool for these different um, use cases. But again, this is sort of a broader survey of what's out there and what sort of we recommend taking a look at as you get started transferring data to and from HPC systems. So I'm going to go through sort of the simplest use case is like if you have data that is publicly available on the internet, you just want to download it to the HP system that you're already sort of logged into. There's a couple tools here we'll cover. And we'll talk about some data integrity, ways to check that the data that you received is actually what you expected or is not corrupted. Talk about data compression and sort of archiving many files, like how to organize your files. And then touch a little bit upon the different data storage and file systems you might interact with, because that'll determine sort of where you actually might want to place the different data that you're transferring to and from a system. And then we'll talk about the specific tools. I'll make a few quick notes about some more sophisticated sort of data distribution networks and federations that are out there that you could use for your project if it seems like that might be useful for you. And then we'll go into the Q&A. And so hopefully, we have about 45 minutes left. There's a lot to cover here, but hopefully you'll find some of this useful. Okay. So the first tool, and it's one that I use almost every day, probably for some reason or another, is wget, right? So this is downloading data from the internet. So it's just a non-interactive data downloader, essentially, right? So if you feed it a URL to a file, it'll grab that file, right? So that's the first example here. You just do wget, point it to, say in this case, I'm pointing it to a data set used for machine learning benchmarking called the CFAR10 data set. And this is how you would transfer that what we call a tarball, and I'll get to that shortly. This CFAR10 python.tar.gz. So we'll talk about the .tar and .gz here in a second. But essentially, it's just a file that's going to get downloaded, right? Now, wget allows you to organize downloads. If you have, say, multiple links, you can put those in a file and feed that file into wget. That's sort of the second example here. So it'll help you manage if you have to download lots of links to different places, if you want to sort of catalog those links and have that sort of catalog available to download to different systems, or just to keep that running catalog available. It's one way to organize what data you have and where it's located, and can also just download it to a given system. And then also, one thing that's pretty useful and find often a lot of users, sort of inexperienced users, have problems with when they first get started transferring data is how to resume a download, right? Sometimes if the data set that you might be downloading is very large, or the file you're downloading is very large, if the connection breaks for whatever reason and you lose the connection, how do you restart that download so you don't have to start from the beginning, right? So many tools will support resuming a download, some do not, right? But you just have to figure out what options are available in the different tools that you might want to use. And if you're downloading or transferring large files, being able to resume the transfer of those files is kind of one of those key features that you're going to want to make sure that the tool you're using has. And so for wget, it's just this -c option, right? Now, there's plenty of other options in all of these tools. These are just kind of highlighting some of the key features that I think are cool and useful, and you would commonly want to use regularly, right? And so that's sort of the idea of these examples that you'll see in each tool. Okay. Curl is a much more sophisticated command line tool that is not just for downloading, it's for doing all sorts of things. It's kind of like a Swiss Army knife of uh, being able to talk to different types of uh, proto protocols over the wire, essentially, right? But by default, it basically does the same thing that wget does. It will use just sort of HTTP, HTTPS GET requests on a URL, right? So this is, you see the first example in curl is the same first example in wget. It's just got one flag, and that's how it's going to download a file essentially that you point to for a given URL. Has the same options to do sort of multiple files, resuming a download, and even you can do downloading multiple files in parallel, which is kind of the sort of more interesting feature that curl supports where wget doesn't, right? So again, this is just a few highlights of the types of things you can do. The first three are same things you can do with wget. I think wget's just simpler if that's all you're doing, kind of these first three. But curl has much more wide set of options for many different things. This multiple files in parallel download is just one of them. Yeah. And then there's things that are a little bit more, like, while curl is very broad in its scope of the things it can do, it's not just meant for downloading data. There are certain tools that are very specialized in downloading data, like wget. Well, this ARIA2 is something less common that you'll see. We have it on our system at SDSC on Expanse, if you're an Expanse user. But the nice thing about this one is it actually has built-in parallelism through multiple connections. So you can basically, essentially, instead of having sort of wget is a serial single connection sort of download, ARIA2 here allows you to specify the number of connections per host that you want to make. And so you can kind of point twice as many sort of network resources effectively at the same URL, and it'll download the file in parallel. So it's a way to, if you're downloading larger files, this is a tool that you might want to look at. It's equivalent to wget, but provides this sort of increased performance, essentially. Okay, so that's sort of a few of the very simple cases. Now, one of the things that's useful to think about when you start transferring data around is, especially, in science, we want to make sure that the data is what the data is, in some sense, right? And data integrity is usually pretty important, especially if you're just copying data around from one place to another, running the same analysis in different places on different HPC systems. You want to make sure that the data that is available that you're analyzing on the system is effectively the same, right? If you are using a data set in one place, it shouldn't be different from the data set in another place, right? And this is preserving the integrity of the data, right? So that the data is always the same. And so, but as you will find over time, sometimes when you're downloading something, connection gets broken or something in your network session sort of gets corrupted, right? You can lose information in a data transfer, right? And the file that you receive might not be the exact same as the one it was that you tried to copy from, right? And so data integrity is something that you want to think about when you're moving data around, right? Are you sure that the data you move from, your lab workbench station to the HPC system, is it exactly the same, right? The source of the data from the lab is the correct version, is the same version copied correctly over to the HPC system, right? For certain types of workflows, this is like very, very important. For others, it may not be, right? So for image data, it's not super important sometimes, like for these simple machine learning techniques, right? And, a pixel off here or there, it's not really going to change the results necessarily for like a classification problem like this. But for other types of problems, it's very important. Now, how do you check the integrity? Well, the simplest way is to use what's called a checksum, right? It's essentially you basically take a piece of data, compute the checksum, which is just an algorithm that feeds in all of the bits essentially of, say, the file and produces a unique fingerprint or ID. This is the checksum, right? It's just a number or a set of characters, some string, the IDs that I fed in this data. This is always the same ID that's produced, right? And this allows you to say that if you run the checksum in one place, the checksum in another place, and you get the same ID, then you know that file is exactly the same, right? On both ends. That's the idea of the checksum. And there's tools like this for on any system. So the most common, one of the most common ones that you'll see out there is the MD5 checksum. And so there's the MD5 sum command line tool that you'll find on pretty much every Linux or Unix-like system. And it computes this hash value. This is the ID that I'm talking about. This is the MD5 hash is what it would be called. And here I'm displaying sort of what the, if you actually go to this CFAR 10 website, right, where the data set, the original data set was posted to the internet, right, they provide these checksums here, right? So they give you the name of the file because there's three different versions. There's a Python version, MATLAB, binary version, different sizes, and they actually post the MD5 sum checksum values, right? So this author of the data set put this on their website so that when you download that file, you can run this tool and check if you get the same ID that you downloaded the data and it was, the integrity data was preserved during the transfer, right? So this is, very common thing that you'll see. This is also used a lot in like software packaging and things like that. So when you're downloading and updating your software on your computer, right? There's usually checksums associated with all those packages that are getting downloaded so that you know that the software is getting installed as correctly. The integrity of the software hasn't been compromised, right? When you're updating your computer. Same thing for data you can use it for, right? So this is just a few command line examples. So you can just, for the MD5 sum tool, you just feed in the actual file that you want to compute the hash of. You can run multiple files through. You can dump the hashes to a file, which is one of the examples here. And then you can actually check and verify those hashes that are stored in a file, right? So if you have the data files and you have the hash file, you can do the check just with this, -c flag on the checksum file, right? So it's a way to organize sort of cataloging all the hashes and being able to verify things as well. So you might see some hash files that you can download as well to verify things. Or you might create some of your own to catalog the hashes. The one thing I have in the bottom here to note is if you are a Mac OS user, there isn't an MD5 sum isn't the name of the tool. There's an MD5 tool. I don't know if they're exactly the same, but the naming convention is different between sort of Linux and Mac OS, but the algorithm is the same. The more common one that you'll start seeing more of these days is the SHA-256 hash. So it's a longer hash. It's a bit more secure than MD5. So the recommendation is usually to use SHA-256 out there these days. So you'll still see both in many places. So I just put the SHA-256 hashes here for the CFAR data set here, which isn't actually posted on the original author's website, but if you wanted to go and download those CFAR 100 data sets, you can check the hashes and see if we get the same ones here. Okay, so that's sort of the basics of data integrity and sort of how to check that the data that you've received through either downloading the data from the internet or between the data transfer tools we'll talk about later. This is how you verify that the data at both ends is the same, right? Okay, data compression. So this is probably something that people are a little bit more familiar with, sort of, through experience in the past, I'm guessing. But just a quick overview, right? Data compression is just the process of reducing, the original data sets into fewer bits so you can save space. That's both on the storage side and on the transmission of the data side, right? And when to apply the compression techniques that you might be able to use really depends on sort of sometimes the data transfer tools that you're using, or how the data is organized already, or you know, uh, sort of what the requirements are, right? Usually you really start thinking about data compression when it's like you have limited storage on different ends, right? And or if the data is large in size, right, it might be a significant saver to compress the data before transfers, right? As you to speed up the total transfer time between systems, right? Um, just one general thing here that I also put was the difference. There's sort of two different types of compression when people talk about compression, right? There's sort of what's called lossless compression. That's usually what we're talking about, right? When we're talking about file transfers, because we want the files on both sides to be the same, right? You don't want to lose any actual information from the compression that you might be using. So that's what's known as lossless compression. Um, but there's also other techniques you'll come across in this example here with the cat is of lossy compression. So any sort of compression technique that you actually like throw away extra bits that you deem unnecessary for, algorithmic reasons, or sort of, you know, for basically you deem some of the information in the data to be less important. Images are the perfect example. It's like, this example shows basically different types of compression from right to left. So basically no compression on the right to like very compressed on the left. And so you can see how you sweep across from right to left that you lose information as you throw away the bits to reduce the size of the image, right? So at some point, you can't really tell it's a cat if you applied maybe the compression to the left, versus if you went somewhere in the middle, you can still tell it's a cat, so it doesn't really matter for, maybe the use case that you're using. So it really depends on the type of data that you have when you're using different types of compression. But in terms of the data transfer, it's always usually the lossless compression that we're talking about. Um, the only thing that I can think of off the top of my head, when we're talking about lossy compression and data transfer, you can think about like, we're on a Zoom call. We're streaming the video out to you all. I'm sure there's some sort of lossy compression algorithms that are being used that are throwing away bits on your between me and you to reduce the cost of the stream, or if you're watching a YouTube video or anything like that, right? There's different levels of uh, um, resolution, right, to the videos, right? That's sort of the lossy compression techniques. Okay. So more of a streaming case, it's usually where you see the lossy compression and that stuff. Okay. So, but yeah, for file transfers, right? There's a few different tools that you will come across very quickly when you start compressing data on HPC systems or on your laptop. gzip is kind of the one that is probably most commonly used, I would say, or the one I use a lot. And I use it indirectly. I'll show you in a second usually. But this is, probably the default one you'll find on any system that you might come across. And so just a few examples here, how to compress a file. Oh, I think there's a typo here. Sorry. Decompress file, right? So here, yeah, the first example is to decompress. So just -d, and I'm decompressing this, cfar10 python.tar.gz, right? So this .gz is the file extension for a gzipped formatted file, right? So you'll see that is the sort of extension that you'll see on a gzip file if you're downloading it, say, from the internet, or if you're transferring it from one place to another, right? The .gz is the indicator for it's been gzipped, right? The .tar we'll talk about on the next slide, which is for an archive file. But so you can then compress the file, which will then add the .gz. That's why there's no .gz in the second example here. You can compress multiple files, right? You can also, with gzip, there's different speeds of compression. Depending on the the type of file and the type of data that's in the file, how much effect that has, I think will vary significantly. And so you can play around with that if you're interested. I've never done too in depth of a study myself, but it's, one of these options that are available that is there, but I don't see a lot of people use. They usually just go with the default. So, but something to explore. Tar. So this is usually how I use gzip. So tar is a command line utility for bundling collections of files. So right, if you have a directory that you want to compress before, say, you transfer it, which is a very common use case, right? If you have lots of files in a directory, it's much better to bundle them together into an archive file, a tar file, and then compress it. You don't have to compress it, but before you do, at least bundle it into a tar file and then transfer it, right? It's much more efficient, especially we'll talk about when we get to file systems and things like that, right? It's much more efficient to transfer a single file that's larger than many small files, right? It's just, think about it in terms of the types of metadata operations that might happen, right? When you have a directory with many files, every time you touch one of those files, the computer is doing something, right? To understand what's in the file and things like that, right? Or the command line tool that you're using to transfer it, every instance of that call to the transfer utility to transfer a single file is a new operation, right? If you can bundle everything into a single file and run that operation once, there's much less overhead, right? And so this is like probably the key tool, if anything, in this section that you want to learn how to use, right? Um, because you can bundle directories together, right? Create a new archive. This is kind of the example here. Create this tar file from this directory, which has however many files it needs, and it'll create a single archive file that you can then transfer. And this is why I said I usually don't actually use gzip directly, because basically there's flags in the tar utility to compress those archive files as you create them, right? So here I'm running the tar command with create with gzip compression, this file, which is what we call a tarball. It should just, anything that's sort of a tar file that's been compressed is usually referred to as a tarball. This is the sort of common terminology you'll see from this directory of whatever data is in there, right? And so there's, tar also has different types of compression that you can use, right? So the second most common one next to gzip is bzip2. That's also built into the tar file, right? Or into the tar command line utility, right? So you can use different types of compression as you create the archive files, right? So it's very convenient. It does like everything that you need in terms of, everyday compression usually, right? There's if your data is, moderately sized, this is sort of the do-it-all utility that you can use for bundling things together and compressing the data. So yeah, bzip2 is the kind of the second most common compression tool that you'll see out there for files that people use. I'm not going to go into too many details. Again, it does everything that kind of gzip does. It's just uses different algorithm, has different compression performance ratios and things like that. You can read about it. I've put the links to sort of everything. All these links, basically go to the Wikipedia pages if you want to dig in more to any of these things and sort of understand sort of what the trade-offs are and how they're different between gzip and bzip2. And so sort of all available here in the links. But of course, and they should be available in the copy of the slides that Cindy passed out. So I'm going to skip the next one just because, well, I'll make a quick note here. I'm going to try to speed up. I'm going a little bit long, I think. There is a parallel gzip. So we have this tool available on Expanse as well. And you'll find this one free. It's kind of like ARIA2. Some systems will have it, some systems won't. Sometimes it's sort of hidden and not necessarily, it might be a sort of built into by default to the tar utility again. And so, but there is a way to do sort of parallel compression. But I think, yeah, the note here is unfortunately the decompression can't be parallelized. So, you kind of get some performance gain in one direction, but it still takes a long time. It'll take a longer time to decompress your archives. Okay, this is the one I was going to skip just because uh, it's around and you'll see it, but it last major release was like more than 10 years ago, so I don't really know if people should be using it necessarily. But the only reason I kept it here is when I was doing research originally on this is it can do both parallel compression and decompression. So you might play around with it, but you probably won't find it too many places, I'm guessing, on different HPC systems at least. Okay, data storage and file system. So remember some of the original questions that I asked is sort of, an important question is, where is the data going? And this is really why this section is here. When you transfer data from, say, your laptop or workstation, right, there's like a local hard drive that usually the files are coming from. Maybe it's coming from some other sort of network file storage, but if you're not familiar with that, your local hard drive is kind of, just the physical medium that's in the in your laptop where the files are stored, and you're transferring it from there to an HPC system. But there's different types of file systems that you'll encounter on HPC systems that you might not have encountered before. And these are all what we call sort of shared network file systems, right? And so they're usually the data when you're transferring to the HPC system, you're not going to sort of a specific node that ahead of time where that data is going to sort of get routed to, right? You're transferring it to sort of an endpoint or a specific node, but then on that node is mounted a file system over the network, which the data will then flow through the network to its eventual resting place. So let me kind of try to illustrate that. I'm going to skip some of these slides here. Yeah, so there's different types of file system, right? So there's yeah, okay, let me go back here. Yeah, so this is kind of the main point that I wanted to bring up about file systems, right? So when you think about the data on your local hard drive, like in your laptop, right? It's going to be on a local file system, right? Where the data is stored, right? Attached to, basically the same computer. In most of the HPC file systems that you're going to interact with when you're transferring data to them or from them, they're going to be usually stored, that data is going to be stored on a distributed file system, right? Where there's many servers that the data might be even sharded across, right? The file might exist on multiple servers if it's large enough, right? And so how you interact with these file systems is important. And that gets to the question about how you organize your data, right? So that's why bundling your data and before you transfer it to an HPC system is kind of the default sort of recommendation, is because usually most of these file systems prefer larger files, larger single files to be dumped on them, because that file might be spread across multiple servers for performance reasons or whatnot, right? And so yeah, and they're very bad usually, most all of them, at these large amounts of small files or large amounts of metadata operations that would be associated if you transferred, say, a directory with like 1 million files in them, right? Because each of those files is creating this overhead of the network traffic because these files are getting, pushed to different servers and all throughout the network where the file system is actually physically living, right? And so that's kind of one of the key concepts of the question of why you need to know where you're transferring the file. Like what type of file system is the data going to land on will determine sort of how you should think about being careful about what type of data, how it's formatted. Is it all bundled together in a tar archive? Or these are the questions of organizing your data before the transfer, and what file system is it going to is kind of one of the key questions that you need to answer before you even think about what tool to use, right? So I just put a list of different file systems you'll encounter. So this is your export file system. So this is kind of like the most common local file system that you'll see on uh, a Linux HPC system. So if you say log into Expanse's login nodes, you might see that all of the sort of operating system for that login node is stored in this type of file system, right? So there's different pieces that will be broken up across different file systems. So the local ones, though, this is kind of the most common one that's running the local file system and the operating system that's on an individual server on the other side, right? The network file system is one of these shared distributed file systems that is commonly used most often for your home directory. So on Expanse, your home directory is an NFS mounted file system, right? So when you log into the login nodes or any of the compute nodes, you can see your home directory there, but your home directory isn't actually on those nodes physically, right? Those nodes are NFS clients, right? Your home directory is visible there because the client software is showing you what's stored in your home directory on the home directory server, right? The NFS server, right? And so again, you can imagine when you start doing lots of file system operations, copies, or start compressing uh, uh, large directories of files or transferring large directories of files between different nodes or different parts of the file system, right? All of that's going over these network calls, right? And that's why you'll notice many times that your home directory is kind of sticky when you're moving around the file system, right? There might be a lot of metadata and network file system calls going on in the background, and it might not just be you, right? Because you share these servers with other people, right? Your file system, your home file system is shared by many different users, right? So someone might be behaving badly on that file system, and it's just affecting your daily, like just LSing and CDing around in the file system, right? And that's because they're not necessarily taking into account that this is causing this sort of contention on the file system is what we would call it, right? So that's why it's important for data transfers to be, try to not create that kind of contention when you sort of dump the files onto your home directory as well, right? So we'll see this a lot, especially with like people setting up Conda environments, right? We get the common questions like, why does it take so long to install my Conda environment in my home directory on Expanse when it takes like, 1 minute on my laptop? It's like, well, your laptop has a local file system with a hard drive right there on the system. Every single installation of every single file in your Conda environment is going into and over the network to your home directory server, right? So it's creating all these calls and creating this huge metadata load that's sort of tying things up. That's why it takes so long, right? So you'll see the same thing when you try to transfer data. Okay, another common file system out there you'll see is Lustre. So this is actually a parallel file system. So it's really meant for writing out and reading in large files in parallel from many different clients. I kind of need to speed up here a little bit. So I won't go into too much detail here, but same idea applies. It's just, you can see here compared to the NFS sort of cartoon model, Lustre and some of these other file systems can get very complicated with different types of servers. Some servers dedicated to metadata versus the servers where the data is actually stored. And then you have all the clients where your compute code is running and then calling to the different servers to find the data. It gets very complicated, right? And you can see how being able to understand what type of file system you're on will really drive the type of performance and characteristics of moving data around on these things will impact your workflows, right? And so being able to understand sort of what the limitations are and what the use cases are for each file system is very important. For example, I'll talk about before we end today, Globus file transfers, right? So our Globus endpoint only transfers data to Lustre, right? One thing that's really nice about Globus is you can point Globus at, hey, I have this directory with 1 million files in it. Please transfer it to the Expanse Lustre Scratch file system. You don't want to do that because it's gonna just same thing like the con environment, setting up a con environment on your home directory. It's just gonna like grind to a halt, right? Because it's really not designed for many small files, right? You really want to bundle that directory up into an archive file before sending it, right? To get the best performance and to not destroy the file system on the other side and impact all the other users, right? So you really want to be careful of like trying to understand a little bit about different file systems and where the data is moving to, right, or from. Another common one you'll see out there these days is Ceph. Ceph is a bit more complicated because it can kind of support many different types of file systems or storage systems available, right? So another reason I bring up Ceph here is because we started using Ceph on a few of our systems, and it also provides something more familiar in sort of the cloud space, like an object-based storage, which is different than traditional sort of POSIX-like file systems, which NFS and Lustre are, right? So the characteristics, if you're using sort of an object-based storage system, if like your HPC system has like a Ceph-based object store, is going to be different, right? It's a little bit better at handling sort of that file problem, but because every file is an object, so it's sort of designed to set up at the object level. And it provides different aspects of things usually, right? So one thing that's really nice about Ceph and that we didn't really talk about here is like when you transfer your data to a file system, you hope that it doesn't get lost there, right? Some file systems, it's too expensive to actually have a backup, right? So like our Lustre file system at Expanse, we don't have any backup of the data you put there, right? You should always keep a copy of the data, no matter what file system. You should always have another copy of your data if it's really important to you somewhere else than on whatever HPC system you're transferring it to, right? You should always keep a backup somewhere because many of these file systems won't have a backup. Ceph is a case where there's a sort of data replication and fault tolerance kind of thing where you can sort of, if like a single drive fails, you're not going to lose data on the file system. It can kind of be recreated and re-replicated, and it prevents data corruption better than say a Lustre file system because Lustre wasn't designed for that, right? So again, thinking about where you want to put your data on any HPC system, right? If you really care about making sure your data doesn't get lost, Ceph would be a better choice than Lustre in most cases, right? In most deployments out there. But again, read your HPC systems user guide, and it should explain like what file system should be used for what use cases and sort of. Again, there's all sorts of practical things like, for example, if you're using Globus on our system, right, you can only transfer first to the Lustre file system, but then you need to move it around to maybe the Ceph file system or to your home directory, which has kind of a limited backup as well. But if you look around in the space and kind of get interested in this topic, or you're working on a different HPC system, there's a whole host of different file systems out there. There's kind of like a zoo and a whole industry of coming up with new file systems these days because of all the problems, mostly around the metadata problem. And you can imagine in the AI machine learning landscape, you have lots of files, lots of small files usually, which has usually been detrimental to these high performance file systems like Lustre in the past, which were more focused on large files, parallel reads and writes. It's kind of a different model in the AI space, right? And so there's a whole host of new file systems that they're trying to solve that type of problem. So you might come across them as well. Okay. 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 Running a little bit long. Okay, so data transfer tools. Okay, so I'm going to go through this really quick because we're at under 10 minutes here. But I think everything, is pretty straightforward here. And you've probably, hopefully, used some of these tools before. If you haven't, this is where you start, right? So SCP is like the standard copy tool, but in most of the use cases in terms of flags and things you might think about using. But for transferring between local systems and your local system and remote systems, right? So here it's just showing a few examples of uploading a file In this case, I'm uploading it to our data, one of our data mover nodes. You can download files from the remote host to your system. You can upload a directory using like a recursive copy, just like you would just with the regular CP command. You can also set up transfers between nodes, so it doesn't have to be only between your local system and the remote host. You can set it up between remote hosts, right? So if you want to do some management work from one HPC system to another, you don't have to first download things to, your system, right? You can transfer between them, which would be much more efficient usually, right? Because there's sort of research networks that are set up between these HPC systems, which you get much better transfer performance most of the time. So you don't have to go through the public internet. Um, and what else? Oh, and of course, there's other options like adding compression as you upload things to you can sort of compress before the transfer occurs. There's these types of options are built into these tools. SFTP is sort of the interactive version of SCP, right? So SCP is sort of, well, you would use in like a shell script or something like that if you want to sort of automate the workflows. But if you really want to just like log into the system, take a look around, see what files are there, and then get a directory or get a file from that remote system, this is how you would do it. If you just want to like peck around and see like, oh yeah, where did I put that file? Like, oh, I need that. This is the tool that you would use for that. So SFTP, you can just log in. It'll give you this, command line prompt, and you can use different things like you can list the files, you can cd to directories, get and put. Get would be the download, put would be uploading a file from your system to the remote system, and then closing out that session. So that's sort of, if you need something interactive, that's like the first tool in line. rsync is a tool that I would say most people, or I mean, many people, when they first get started, don't start out using. They kind of start off with SCP and SFTP. But if you have lots of files that you need to sort of synchronize between systems, this is the tool you want. Think about it sort of like your manual Dropbox command between two systems, right? So you can sort of just take a directory and have it sort of completely get copied over, and it does it in a synchronization type fashion. So it's not going to transfer every file. It's going to figure out what files that are in that directory that might not be on the remote system that need to get transferred over. So it's not going to copy everything over again that might already be on the other system. So if you need to keep data between systems synchronized as part of your workflow, this is the kind of the tool that you want to use, right? And again, there's tons of different options. There's even different types of recursive options here that I'm showing between the -R and the -A. If you need to preserve timestamps on the files and things like that, there's options for that in here. And again, also turning on compression before the data gets sent. This is sort of, if you need to really automate synchronizing files across system, this is the tool that you want to use, up to a certain extent, right? So most of these SCP, SFTP, rsync, if your data set size or your data sizes are reasonable, up to, I don't know, 10 gigabytes in any sort of transfer, this is going to be, or maybe a little bit more, is going to be like a reasonable approach to getting your data to and from HPC systems. If you have significant amounts of data, though, Globus is kind of the tool that you're going to want to use, right? So if you have terabytes of data, this is kind of your only option to really move things around. And so it's based off of grid FTP is kind of the protocol, which is basically parallel FTP type of protocol, but it's sort of been developed over the last 20 plus years or so, maybe longer now, 25. And it's been sort of spun out into a nonprofit sort of company run by the University of Chicago, where it originally started. So the Globus itself offers a bunch of other services now in terms of also like compute services and things. But the original is really the file transfer service. And so you can kind of see here, I'm showing They have a nice web app that you can log into and point the web app at the different, what they call Globus endpoints or collections these days. You can see here on the left, I have our Expanse collection on the Expanse Luster file system, and I'm transferring some files here to the Ohio Supercomputer Center on their GP, IBM Spectrum Scale GPUFS file system. Anyway, so there's different file systems on both sides, but they both have Globus endpoints, and so this is what I'm using to move a large data set or my data sets file from Expanse over to OSC, right? So there's probably, I don't know, at least a few terabytes of data in there, right? And I can just select all of those sort of uh, directories or individual directories at once and just hit click and start, and Globus will manage everything that you can think about. It'll do the checksums. It'll do setting up parallel connections. It'll do the most optimized way to transfer the data from one endpoint to another, right? And, I think the largest transfer I ever did was like maybe 8 terabytes or more in one sitting, if I remember correctly, maybe 10, it was 10 terabytes, but it took about 8 hours, I think, from like Berkeley lab to Expanse at SDSC. Anyway, so it's like the best way to move large amounts of data, and it does all the nice things about data integrity, parallel connections, and things that I've touched on with some of the other tools, and compression and things like that, right? But it kind of just magically works. They also have command line tools. If you want to do Globus transfers from your personal laptop or desktop, they have like you can set up your own Globus Connect personal endpoint where you can set up your own sort of transfer specifically to your laptop to, say, an HPC endpoint. You can do all that with the software that they offer. So if you've never used Globus and it sounds like it's something you might want to use, I would highly recommend checking out. It's quite good. Um, let's see, I'm running out of time. Oh, I'm over. Okay. So there's all sorts of other tools you'll come across on the HPC system. Open on Demand is what's sort of known as a web portal for accessing HPC systems. These, if you log into an HPC system through like a web app, usually there's a file transfer option, so you can upload directly through your web browser, just kind of why I highlighted this here. Similar if you're like using Jupyter Lab or something, right? It has a file transfer mechanism sort of integrated to the file browser, right? So if you just want to upload a file from your system to your Jupyter session on an HPC system, that's, completely reasonable. Again, it really comes down to how much data you're talking about, right? Like Jupyter Lab and Open On Demand, these things are not going to stand up to terabytes of data if you try to upload it through their file browser, right? It's just not going to work. Right? That's when you have to use Globus. So these are the trade-offs that you have, but these are all the options, right? If you're just, editing, a few hundred megabytes of data files in sort of Pandas and analyzing it, uploading it through Jupyter Lab is completely reasonable, right? Oh, and one last tool that I haven't got back to putting some examples on or just mentioning more about it is rclone. I've started using a lot more. It's very good for if you're doing any work with cloud-based storage, right? So like Amazon's S3 service or other object stores. This is kind of like a tool that does a lot of the similar things that you can get with rsync, synchronizing sort of data on your system to, say, Amazon's S3 or an OpenStack object storage service. There's Swift object storage. If you're doing any sort of object storage stuff, rclone is kind of the tool that you're either familiar with if you're already doing it. If not, and you need to find a tool, this is the one that I think I would recommend. Okay, so I'm over time, and give me 2 more minutes if you're still here with me, and I will just mention briefly these open data distribution networks that you can get access to if you need to, right? So there's sort of three that I want to mention. There's the Open Science Data Federation. So this is a set of basically places where you can upload data, these origins, and where these origins will then sort of allow your data to be accessible across different caches around the country or around the world, right? So Many HPC systems have caches nearby that might also you might be able to access your data from, right? So, I've done some experience in the past where I had data stored over in Chicago and one of these origins I have access to here, and it was doing sort of machine learning training on the data from SDSC on Expanse. And you can see here we have a cache nearby. So as I was basically iterating through this training run, right, you could see that the performance was increasing as the data got cached closer and closer and closer to San Diego, essentially. Like basically this cache is either in the same data center or across campus, I forget. Um, but if you need to sort of, if you're using the Open Science Grid, if you haven't heard of that before, right, the OSDF is sort of natively integrated into the Open Science Grid, and this is how you can easily transfer, get sort of data distributed to any sort of compute part of the Open Science Grid infrastructure that's available out there. So it's, um, again, it's sort of a part of the service that's provided. Now, of course, if you have like lots of data, if you have like terabytes and petabytes of data, that you have to sort of talk to them and ask like, hey, how much space can I get in these caches for my project and so forth. It's sort of a more of a social engineering problem at that point. But if you have a couple terabytes of data, it's not too hard to get space. Similar type of project is the Open Storage Network, sort of trying to solve a similar problem of like how do you deploy storage across the sort of cyber infrastructure available to researchers in the country. You can get an allocation of storage on the Open Storage Network and sort of make that sort of available. I think it's more like a more object storage oriented is my understanding, but I haven't played around with it myself yet. But it's another type of data distribution network that's out there. And similarly, there's sort of a more overarching umbrella project called the National Science Data Fabric, which sort of, if you look at the bottom of they have sort of their own tooling that rides above many of these other data transfer mechanisms. And even in this picture, you can see that they talk to both the OSDF network and the OSN network. So it's sort of a broader sort of umbrella project trying to ride atop more of the infrastructure that's available out there. So it's just another project out there that you might want to check out if this type of sort of data distribution network sounds interesting to you. Okay, and that's it.